All right, guys, make sure you have your notebook and your data booklet out, something to write with, and let's get started. So open your data booklet to page 5. Let's define these equations. This is the equation for momentum. The symbol P, this is momentum. Momentum. It is a vector. M is mass, and mass is in units of kilograms, so mass in kilogram. V is velocity, that is in meters per second. So the units for momentum are kilogram times a meter times a second to the -1, kilogram meter per second. And it is a vector. It has a magnitude and a direction, either positive or negative direction. We have Newton's second law rewritten, where force is equal to a change in momentum over a change in time. And then we have an equation for kinetic energy. Kinetic energy is equal to momentum squared divided by 2m. So we're going to skip that last equation and save it for the next video on impulse momentum theory. We're just covering momentum in this video. So Newton's second law in terms of momentum is this. Linear momentum, symbol P, is defined to be the product of an object's mass with its velocity. So mass is a scalar, velocity is a vector. A scalar times a vector gives you a vector. Its units are obtained again from the formula, and they are kilogram meter per second. It is a vector, I must stress this. Momentum has direction and magnitude. So from Newton's second law, we can get this equation. F net is equal to mass times acceleration. That's what you see right here. And if we know that acceleration is a change in velocity over a change in time, together this is acceleration, I can substitute out, I can multiply mass directly by change in velocity and divide by the change in time. And what you see is mass times a change in velocity is the same thing as a change in momentum divided by change in time. So Newton's, when he wrote this Principia, this book on motion, he actually included momentum as part of the derivation. F net is equal to delta P over delta T. And then very quickly, you can get kinetic energy in terms of momentum. This is out of order. Okay, momentum is equal to mass times velocity, and if we square momentum, we get P squared equals m squared times v squared. And I know E sub k is equal to 1/2 mv squared, so I can substitute out the mass and the velocity for P squared, multiply by 1/2, and divide by mass. Therefore, the 3 dots, that triangular shape is therefore we get E sub k equals P squared over 2m. You don't have to know this derivation, but there it is. All right, let's talk about a collision. A collision is an event in which a relatively strong force acts on two or more bodies for a relatively short amount of time. In the absence of any external forces, momentum is conserved, no matter what type of collision. And here we can see this beautiful crater located in Arizona. This resulted from a collision between the planet Earth and a meteor. So let's consider two pool balls, and they're on a billiard table, and they collide with each other. This is a collision, and so what you need to do, you analyze the momentum of the system before collision, just before the moment these two objects collide. This is our before phase analysis. Then we have during phase. We'll get more into the during part during our impulse momentum theory. That's the next video you guys will watch. And then you focus on what happens to the two objects just after collision. So 3 parts to this: before, during, after. For conservation of momentum, we focus on just before and just after. This is known as a system boundary, the place that's boxed in with these dashes. It's the area of interest. And physicists use systems in the study of very complicated processes. We don't want to know everything that's going on with the pool table or potential forces lost there. Things can get really ugly really quick. So you just try to keep it as simple as possible and focus on the system. The system are the objects in collision. And a closed system has no work done on it by its external forces. If there's no external force, momentum is conserved. All right, two main types of collisions are elastic and inelastic collisions. So elastic collisions occur when objects collide, but they don't stick. So imagine those pool balls, the billiard balls, they collide with each other, they don't make a sound, they don't lose any energy. It's a perfectly elastic collision, and they just bounce right off of each other. In that case, momentum and kinetic energy are conserved. Another way of saying things are conserved, the change in momentum before and after collision is 0, and the change in kinetic energy before and after the collision equals 0. So for momentum, P final, the sum of all of the final momenta minus the sum of the initial momenta should equal 0. Same thing for the kinetic energy before and after collision. The sum of EK final minus sigma, the sum of all of the initial kinetic energy, EK initial equals 0. This is true only for perfectly elastic collisions, which are the main type of collisions you'll deal with in the course. Second type of collision are inelastic collisions. So this is where objects collide and stick together. How do they stick together? They lost some kinetic energy. There was work done to the objects to cause them to stick, to cause some deformation. Sound energy, heat, light energy, if there were sparks flying. Post-collision, the objects will have typically less kinetic energy than what they started with. So E sub k, delta E sub k does not equal 0. But no matter what, the delta P will equal 0 as long as there are no external forces acting on the system. Explosions are similar to completely inelastic collisions in that these bodies, whatever this explosion is made of, these bodies were originally stuck together and then they spread outwards with the same velocity. Okay, so the change in kinetic energy does not equal 0. For an explosion, you'll have a positive change in kinetic energy, but the change in momentum is 0. So change in momentum is 0. That means momentum is conserved. How could that be possible? Momentum is a vector. So let's say I did have, I don't know, some sort of bomb, okay, and this bomb blows up and it sends material out in all these directions. This side would be the negative direction for momentum, and this side would be the positive direction for momentum. If we were to add up the momenta of all the pieces, including the direction, you would find that the momentum after this explosion also equals 0 because the directions cancel out. The masses of all these pieces times their velocity with the direction, everything cancels, so the momentum is conserved for explosions. Practice problem number 1, I ask at the very least that you draw the picture here, any pictures, and then you're going to show your work and then give me the final answer. Box it in, please. You're going to upload your notes for the 5 practice problems we're about to solve, and that's how you'll get credit for watching this video. So 2 objects, mass 1 and mass 2, approach each other along a straight line with speeds v1 and v2 as shown. They collide and stick together. What is the total change of linear momentum of the objects as a result of the collision? So we have our system boundary here. The system includes both objects. They're going to collide. They're going to stick together. This would be an elastic collision. And because I'm analyzing this system, I'm analyzing both objects that are colliding, the total change of linear momentum should be 0 because no matter what, as long as there are no external forces acting, momentum is conserved. A ball of mass m travels horizontally with speed v before colliding with a vertical wall. The ball rebounds at speed v in a direction opposite to its initial direction. What is the magnitude of the change in the momentum of the ball? So I like to draw a picture. Here's my wall, vertical. Here is a ball. It is coming in with some speed v, and this is before collision. and then it's going to rebound with some speed v after collision. What is the change? What is the magnitude of the change in momentum of the ball? And a lot of students on this question said, okay, momentum is always conserved in a collision in the absence of external forces, so delta P is 0, and they would be wrong. Sorry about that. Alarm's going off here. Okay, and that is because we are not analyzing the entire system. Then the system, for the system, delta P does in fact equal 0. This is true, but we are not analyzing the system. And by the system, I mean the two objects that are colliding. For both the momentum, delta P for the wall and the ball would equal 0. So if we analyze the two objects that were in collision, the ball and the wall, you would find that yes, indeed, the wall would have a very minute change in its velocity. The ball has a much larger change in its velocity because it has smaller mass, and if we added up the final momentum for both minus the initial momentum of the ball, that difference would be 0. But we are not analyzing the ball and the wall's momenta. We are just analyzing the momentum of the ball. So in this case, delta P is not 0. We're not analyzing the entire system. So delta P for the ball is non-zero. Delta P for the ball only does not equal 0. Okay, so we will get P final for the ball minus the ball's initial momentum, and this will equal our non-zero delta P. And the key to this is remembering that momentum is a vector. So I'm going to choose this direction to be positive, and I'm going to choose the left direction to be negative. Okay, so, and the ball has mass m. So for our final velocity, I have negative m times v minus the initial momentum, the final momentum is negative m times v, that's the mass, times its speed with direction. For the initial momentum, I have mass times a positive v, because it's going in the positive direction. Mass negative m times v minus m times v, this is equal to negative 2m times v. But they want the magnitude, so I can just take the absolute value, or I just record the positive answer, 2mv. So you can see the change in the ball's momentum does not equal 0 because we're not analyzing the wall's change in momentum, or you could look at it like the wall exerts an external force on the ball, so there's a non-zero change in the ball's momentum. All right, here we go, another ball striking a vertical wall problem. And this ball of mass m strikes a vertical wall with a speed v at an angle theta to the wall. So please copy this diagram right here. Here's the ball coming in with an initial speed v, and here's the ball leaving with a final speed v, and you have the angle with respect to this normal line, this line that is 90 degrees with respect to the vertical wall. Then they want to know, okay, the ball rebounds at the same speed and angle, so what is the change in the magnitude of the momentum of the ball? And the ball experiences an external force. That force is applied by the wall. Delta P then, for the ball, does not equal 0. There is a non-zero change in the ball's momentum. The ball's momentum is not conserved because it experiences an external force exerted by the wall. Also, these two objects are colliding. A ball and a wall are colliding. As such, we are not analyzing the entire system here. We're only analyzing one part of the system, only the ball that's colliding. So we will not have a non-zero change in momentum. In this case, momentum is not conserved because we're just looking at the ball, but if we could look at the momenta for both the ball and the wall, delta P would equal 0. But they don't ask that. They want just of the ball, so it is a non-zero change. Do not put 0. Okay, so let's figure this out because momentum is a vector, and now you're asked to analyze momentum in 2 dimensions. You will do this a lot in college, and the problems will be harder. In fact, you will be doing this in 3 dimensions as well. So the key here is that you will find the change in velocity for the x direction. You'll find the change in the vertical velocity in the y direction, and for 3D, you will find the change in the z direction. But for now, we just focus on x and y. We will break these vectors, the initial velocity vector and the final velocity vector, these two, into their vertical and horizontal components. I'd like to analyze them graphically, and then we will analyze them mathematically to get the answer. So I'm going to split this initial velocity vector into its vertical component. Oops. V y initial is like this. And then it has this horizontal component. I'll do it in purple. This is Vx initial. So the ball is coming in at an angle towards the wall. So it goes down and to the right. When the ball rebounds, its final velocity in the y direction is also down, Vy final, and its final velocity in the x direction points out of the wall, Vx final. So we will get the change in this object's vertical velocity, and we will get the change in the object's horizontal velocity. And of course, in more advanced classes, you would recombine all of your directions using the Pythagorean theorem. In this case, we won't need to. Let's get the change in the object's vertical velocity, the change in the y direction first. So delta V sub y is Vy final minus Vy initial. If I analyze this using the vector method, or by drawing the vectors out, I see that this Vy final vector points down. And then I'm going to subtract this Vy initial vector. And if you remember from our head to tail method of adding or subtracting vectors, when you subtract a vector, it is the same as adding the opposite of that vector. So this vector points down, the Vy final points down, so I will add it to this vector, but it points up in the opposite direction. The opposite direction is like subtracting. You add the opposite vector, so they have the same magnitude, these two arrows, opposite direction, so they cancel out. They equal 0. So in the case of this collision, the ball's vertical velocity does not change. Let's now look at its horizontal velocity. Delta V sub x. Delta V sub x will equal its Vx final minus its Vx initial. Trying to keep with the color scheme here. Vx initial. Same thing, I'm going to do it graphically. I'll do this vector addition graphically. So this arrow points to the left for the Vx final, minus this purple arrow that points to the right. So the purple arrow, positive Vx initial, points like this. So if I want to subtract that vector, it is the same as adding the opposite. So negative Vxi would be like this, points to the left. So I now get a vector that is non-zero. It is a longer vector. It is the sum of the two together. Now, we're not going to answer an exam question with arrows and symbols like this. Okay, some of the questions you'll do some arrows, but in this case, let's rewrite Vxf and Vxi in terms of known values about the vector triangle, about the speed. So looking here, we have this total magnitude of V initial coming in like this at some angle theta, and I want the Vx initial. This V initial is the hypotenuse, and this Vx initial is adjacent to the angle. It touches the angle. So I have an adjacent and a hypotenuse. If I state the mnemonic device, so ka toa, ka, c, a, h, that's cosine theta equals adjacent over hypotenuse. So my Vx initial is equal to V initial times cosine theta. I can do the same thing with this vector triangle here. Vx final is equal to the final speed, V, cosine theta. Now, velocity is a vector. It has magnitude, it has direction. So if I choose the right to be positive, the left to be negative, then my change in velocity vector, negative V cosine theta minus V cosine theta, delta V sub x is equal to negative 2 V cosine theta. Non-zero here. But they want the magnitude, so I don't have to worry about my directions. If they want the magnitude, you take the absolute value. So the change in the ball's velocity, its total change, is just the x direction. The x direction is the only part of the velocity that survives. Delta V is equal to 2V cosine theta. There is no y component difference in the velocity, and they want the momentum, so delta P, you just multiply by the mass, 2mv cosine theta. Very fun problem, just takes a little bit of vector analysis. All right, I promise we're almost done. Problem 4, the momentum of a particle stays constant provided that, is it A, it moves in a circle with constant speed, B, its acceleration is uniform, C, the net internal force acting on it is 0, or is it D, the net external force acting on it is 0? Please put your answer. A moving system undergoes an explosion. What is correct for the momentum of the system and the kinetic energy of the system when they are compared immediately before and after explosion? Explosion is just like the opposite of an inelastic collision. Momentum is conserved. But you could imagine immediately after an explosion, think of a bomb going off, what happens to the pieces of that bomb? Do they move faster or do they move slower than before? That should help you narrow the last 2 answer choices down. Put your answer, take a picture of your practice problems 1 through 5, and upload them to the One Notebook. Thanks for watching, guys, and study well.